Okay, well, welcome everybody, and welcome to the virtual seminar of the International Institute of Physics in Natal. And it's a great pleasure to introduce today our speaker, Douglas Stanford from Stanford University. Doug graduated from Stanford and he received his master's from Cambridge and his PhD from Stanford. After his PhD, he went for 5 years to Institute for Studies in Princeton. And since 2019, he is a faculty at Stanford. Doug is working in string theory and quantum gravity, and he is very well known for contributions to recent advances in understanding physics of black holes. And for these contributions, in particular for connecting quantum physics, black holes, and the theory of chaos, he received several prestigious awards, including Griebel's Medal of the European Physical Society and the New Horizons in Physics Prize from the Fundamental Physics Prize Foundation. Today, Doug will talk about quantum physics, quantum black hole physics, and I would like to thank him for accepting our invitation. Welcome, Doug, and the word is yours now.
Okay, thank you. Thanks very much for the opportunity to give this talk. Okay, good. So this is a talk that I've given a version of twice before, and I think it's online. So the real advantage to my presenting it here and discussing it with you folks is the discussion we can have. So please do not hesitate to ask questions, interrupt me anytime. You can, I don't know, type a chat, or raise your hand, or just unmute yourself and just shout. And I would really appreciate that. So please feel free. Okay, so all right, let's get started. So there's an amazing idea that has been driving progress in high energy theoretical physics for a few decades now, which is this statement here in the red box, the statement that from a distance, a black hole behaves like an ordinary quantum system with many degrees of freedom and strong interactions. So what that means is it's supposed to mean that if there's a black hole somewhere and you are in a somehow a black hole in a somewhat controlled environment where you can throw things into it and measure what's coming out, you can analyze it like a conventional experimental system, then the results of experiments you would do on it would be consistent with the thing not being a black hole at all, and instead being a conventional quantum system, although one with many degrees of freedom and strong interactions between the degrees of freedom. So this is a conjecture, and it's passed many tests over the last couple of decades. Basically, the way a test works is that people think of something that an ordinary quantum system should be able to do, or property that it should have, and they check to see if a black hole does that. So these things, examples of tests that have been passed include studies of thermodynamics, black body radiation. This is Hawking's calculation of Hawking radiation. Thermalization of perturbations. This is one of my favorite ones. Transport phenomena, including superconductivity, quantum chaos, and the dynamics of entanglement, dynamics of quantum entanglement. So these tests, if you look at them, are sort of increasingly fine-grained, increasingly quantum properties that somehow black holes reproduce in simple and surprising ways. Okay, so this is a real triumph. But there's a few properties of ordinary quantum systems that black holes have not so far been able to replicate. So by looking at the space-time description of a black hole, we can't see obviously that they have all of the properties of an ordinary quantum system. And roughly speaking, these problems go by the name of the black hole information problem. In the last few years, some progress has been made on understanding aspects of these problems, although it's not finished. We have the task is not finished. But there's been some progress, and space-time wormholes or spatial wormholes play a leading role in that. So I'm going to discuss three examples of that in this talk. Three places where wormhole effects help black holes reproduce ordinary quantum mechanics. Okay, so the three examples we'll discuss are ER equals EPR and quantum teleportation. The second one is random matrix universality. The third one we'll just discuss very briefly the entropy of Hawking radiation. Okay, so that's the plan. And again, please interrupt me whenever you like, and it will be better for all of us.
Okay, can I ask a question?
Yeah,
so
please.
how distant you have to be? How do you measure this? You mentioned the conjecture that for distant.
Yeah.
But it's possible to do to compute those corrections or to it.
Right. So the most precise version of this is for a case where the black hole is kind of confined inside anti-de Sitter space, and the measurements that you do correspond to changing the boundary conditions of at the boundary of anti-de Sitter space. So you can throw in particles from the boundary, you can absorb particles from the boundary. That's the most controlled case, and that's the one where the black hole is literally supposed to be a description of a quantum system. But it's believed and to some extent tested that it should be also true if you think about a black hole in a less perfect box than anti-de Sitter space. So, for example, if you're just a few Schwarzschild radii outside the black hole, and you imagine putting some kind of a detector, some kind of Dyson sphere around a black hole, just a few Schwarzschild radii away, then a description of that system by a quantum mechanical system should be good. You might just have to also include a little bit the interactions between that system and the gravitational modes and fluctuations of the detector and so on. So,
okay.
The basic answer to the question is that the most depends how precisely you want the statement to be made. If you want it to be made very precisely, then the observer should be infinitely far away at the boundary of anti-de Sitter space. But if you're okay with a somewhat less precise statement, then just a couple of Schwarzschild radii should be okay.
Okay, thank you.
Yeah, thank you for the question. This is actually something people debate a little bit in the literature. I've given you my view on it, but other people have a different view that if you have finite cutoff, then the story really changes qualitatively.
Thank you.
Okay. Okay, so the first thing we're going to discuss is an example of a black hole exhibiting an effect that ordinary quantum systems can exhibit, which is called quantum teleportation. I'm going to start by explaining what quantum teleportation is, and then we'll see how black holes accomplish it using wormholes. So quantum teleportation is a protocol that was invented reasonably recently in 1993, long after the invention of quantum mechanics. And it's a protocol that allows Alice over here on the left to communicate a quantum state psi to Bob. And the rules are that Alice is not allowed to just hand the quantum state to Bob. She can like call him on the phone and tell him classical information, like things that you could actually say over a phone. And it sounds very hard to send a quantum state under those circumstances, because quantum states are hard to encode in classical information, for one thing. But also, Alice may not actually know the quantum state psi. It's just the quantum state of some physical system she has in the lab. She might not know exactly what it is. And if she tries to measure it to tell Bob what it is, she might change it. So it sounds like it's going to be very hard to communicate the state. But the kind of miracle that these authors discovered is that Alice can do this as long as she and Bob share in advance some entangled code books, some entangled state. They can use that as a resource to accomplish this task. And the rough structure, I'm not going to go through the details, but the rough structure of the protocol is the following. Alice takes her half of the entangled system, that's this book, together with a quantum state, and she does some joint measurement on those two systems. She gets some outcome, let's say the number 3. She then calls Bob on the phone and says that the answer for the measurement was 3. And Bob can use that information together with his half of the entangled state. So his entangled codebook, he can put that into a different machine, and out comes the state psi. So I haven't proven that to you, but that I haven't explained exactly how it works, but it works, and it's kind of a beautiful quantum mechanical protocol. Uses entanglement between these code books plus classical communication, just saying the number 3 to send the quantum state psi from Alice to Bob. Okay, so this is all I'm going to say about quantum teleportation. But let me just leave sort of a philosophical sounding question here, that this picture does not make it very obvious what it would feel like if you were the quantum state that was being teleported. And among other things, the wormhole description of quantum teleportation will give us an answer to that question. Okay, so what are we going to do now? Well, if entangled codebooks are a resource that allows us to power quantum teleportation, what type of resource is a pair of entangled black holes? So remember, the idea is that black holes are, the conjecture is that the black holes are really ordinary quantum mechanical systems. And if you can take entangled ordinary quantum mechanical systems and use them to accomplish a task like quantum teleportation, the natural question is, can you do the same thing using entangled black holes? Okay. So here's the idea, that ER equals EPR conjecture of Malthus and Susskind gives an answer to what type of resource entangled black holes are. So this is a picture of space if we have a pair of unentangled black holes. So black hole A, black hole B, with rocket ships outside both of them. And they're 2 separate interiors. If the black holes are entangled, then the idea is that the interiors are connected by a wormhole, so that the spatial geometry of 2 entangled black holes would be this one. There's a connection outside the black holes here, outside the horizon, so you can just go from near one black hole to near the other one, but there's also a connection behind the horizon of this wormhole. So this wormhole is somehow supposed to be the resource that's associated to making the black holes entangled. Okay, so we're going to draw this geometry on the next slide a little bit more precisely. And in order to make it possible to draw in a convenient type of diagram, I'm going to simplify the geometry by cutting the space that is between the outsides of the black holes. So after we cut this space, then the only connection between the 2 sides is through the wormhole. The only connection between the 2 sides is behind the horizon of the black hole. That's just going to make it easier to draw the space-time. And to compensate for the fact that there used to be a spatial connection outside the black holes, we're going to allow Alice and Bob to communicate with each other using a phone call. So that's the rule. And they are going to try to use this wormhole to accomplish quantum teleportation. All right, so here's the diagram that I promised to show you. This is a more precise space-time diagram of the 2 black holes and the wormhole connecting them. So time goes up, space goes sideways, and the region out here on the left, this is a space-time region that is outside Alice's black hole. And the region over here is the region of space-time that is outside Bob's black hole. So, whoops, so here are Alice and Bob. They are on rocket ships outside the 2 black holes. So Alice is accelerating to the left to stay outside her black hole, and Bob is accelerating to the right to stay outside his black hole. And the gray region here is behind the horizon of the 2 black holes. A horizontal line straight through this diagram corresponds to the space of that wormhole we drew on the previous slide. So that's this wormhole here, is the horizontal line through the diagram. Okay, and the zigzag line in the future inside the black hole is the space-time singularity, where the space-time of the black hole ends, space-time of the wormhole ends. Okay, so that's the space-time geometry that is related to these 2 entangled black holes. So let's try. let's try to accomplish quantum teleportation using this resource. Well, the first guess is that if Alice wants to send a quantum state to Bob, what she should do is she should just try to send it through the wormhole to Bob. So that's what we're trying to do here. That's the red line. So at an early time here, Alice takes the quantum state and she sends it into the black hole. She sends it as fast as it can possibly go, which is a speed of light. And the rule of this diagram, space-time diagram, is that light rays move on 45-degree lines. So this red ray here represents a light ray. It represents a light ray that is the trajectory where the state psi is propagating. And unfortunately, it doesn't make it out to the right side. As you can see, it's behind the horizon of Bob's black hole, so it remains in the gray region and it actually hits the singularity instead of making it out to Bob's spaceship. So this doesn't work. Alice, no matter how hard she throws the rock from her side of the wormhole, it will not make it out to Bob. So this is what's called a non-traversable wormhole. So, and in the paper by Malvasena and Susskind, they make a kind of profound point that the non-traversability of this wormhole is related to the fact that you cannot use entangled states by themselves to send signals. So if you and I share an entangled state, and I'm on Alpha Centauri and you are here on Earth, then there's nothing that you can do to your quantum state that will instantly send me a signal on Alpha Centauri. And that's related here to the fact that you cannot send a signal through the wormhole. Okay. Okay, so they need to do something a little bit different. Alice can do something slightly different and make the traversable wormhole protocol work to enable quantum teleportation. So this is a protocol that was invented by Gao, Jeffers, and Wall. And here's how it works. So we start out exactly the same way. Alice throws her quantum state into the black hole, and by itself, we know that is not going to work. But she does something else a little bit later. A little bit later, she measures a piece of Hawking radiation that has subsequently come out of her black hole. She just measures any old piece of Hawking radiation, and she communicates the result to Bob using the telephone that we allowed them to have earlier. So the measurement of the Hawking radiation causes a little bit of a disturbance in the quantum fields outside the black hole, and it causes a little bit of positive energy to fall into the black hole. That's this red squiggly line. So measurements in quantum mechanics are generally cause excitations, and the measurement that she's doing here, her Hawking radiation, causes a little bit of extra energy to fall into the black hole. Okay. Now, based on the results of that measurement, it turns out that Bob is able to apply an operation on his side of the black hole that sends in negative energy into the black hole interior. So this is just a property. This isn't really anything that has to do with black holes. It's just a property of quantum field theory that if we have two points that are close together in space, and if we consider the vacuum state, then if somebody measures the fields at their location, if Alice measures the fields over here, and then Bob, in principle, could use that information to lower the energy of the quantum state a little bit, lower the local energy below the vacuum value. That relies on the fact that there's entanglement between the two nearby regions in quantum field theory. So anyhow, that means that after Alice measures her piece of Hawking radiation, communicates the result to Bob, Bob can do a measurement, can apply an operation outside his black hole that will introduce a small amount of negative energy that falls into the black hole. There's positive energy coming in from the left, and there's negative energy coming in from the right. And you might have heard of a famous effect in general relativity called the Shapiro time delay, which says that light rays are delayed by the existence of matter in between the emitter and the receiver. So the gravitational potential slows down the light rays a little bit. That's if you have positive energy. But if you have negative energy like we have here, it's exactly the opposite effect. So light rays have an advance. So they come out a little bit earlier than you would have expected without the matter there. Geometrically, you can represent that by saying that the light ray is traveling along at 45 degrees. And as it crosses the negative energy, it has a time advance. So it crosses and comes out a little bit earlier than you would have expected. So a lower point on this diagram corresponds to an earlier time. Okay, and incorporating that effect, the red trajectory makes it out to Bob's spaceship on the right side, which means that the quantum state psi has made it through the wormhole and made it to the other side. So this is the quantum teleportation protocol. And okay, so what is the answer to the question we started with? What is the resource associated to two entangled black holes? The resource is a wormhole that connects them. How does this help the black holes to accomplish the task of quantum teleportation? Well, the message goes through the wormhole. And finally, we can answer this sort of philosophical question: what does it feel like to be teleported? What does it feel like? Well, this red state, this quantum state psi, is just in free fall here, falling across a wormhole, basically in inertial motion. And the interaction with this negative energy here also can be inertial. So the quantum state psi basically doesn't feel anything. It just feels like it's floating in empty space. So it's a perfectly pleasant experience. The thing I want to emphasize about this example is I said at the beginning that black holes often accomplish tasks of ordinary quantum systems in simple but surprising ways. And this is a nice example of that. The quantum teleportation task is accomplished in an incredibly simple way. The particle just goes through the wormhole, so you can kind of see it propagating from one side to the other. It's a very clear and very simple presentation of quantum teleportation. Sort of the quantum mechanical protocol and the entanglement are encoded in the space-time geometry.
I have a question. So can you relate this protocol with some standard protocol of quantum teleportation? Or is it some kind of a new protocol? I mean, certainly since you referring here to some properties of quantum field theory, you probably can write it in terms of some quantum protocol.
Yeah, so it's well, it depends a little bit on your perspective, whether you consider this an example of ordinary quantum teleportation or a somewhat new protocol. But probably the most precise thing to say is that it's a somewhat new protocol for quantum teleportation, and people have referred to it as many-body quantum teleportation. Many-body quantum teleportation protocol, where you basically just add a quantum state add the thing you want to teleport to an entangled quantum state, and then you just measure anything a little bit later. That's like measuring the Hawking radiation a little bit later. And actually, there have been some proposals that have been partially carried out experimentally to realize this protocol in near-term quantum devices, which are able to behave like interacting quantum systems. So there's a group at Google and another group at Harvard and Berkeley that have proposed experiments to understand this kind of slightly new version of quantum teleportation.
Okay, thanks.
Yeah, thanks for the question. Okay, so the second example of wormholes helping black holes accomplish quantum tasks is random matrix universality. So this is a completely different topic now. We're changing gears entirely. And we're going to change gears one more time again. So this is part 2 of 3 parts. Okay, so if it's true, if this conjecture is true, that black holes represent ordinary quantum systems, then one obvious thing is that they should have a discrete set of energy eigenvalues. Finite entropy, ordinary quantum systems have a discrete set of energy eigenvalues. That's, in some sense, the most quantum data that a quantum system has, is the spectrum of energy eigenvalues. Okay, so the question is, how does a smooth continuous space-time, like the description of a black hole, how does it produce a complicated discrete list of numbers like the set of energy eigenvalues? And okay, this is one of these things where we don't know the answer. This is a version of the black hole information problem that has not been solved. We don't know where this discrete, complicated information comes from of all of these energy eigenvalues. However, we understand a little bit. So here's what has been understood so far. So black holes thermalize very rapidly. They thermalize perturbations very rapidly and they exhibit the butterfly effect. So to the extent that they represent quantum systems at all, they must represent chaotic quantum systems. And chaotic quantum systems are supposed to have kind of an amazing property. This is an old and famous idea in physics, that the statistics of energy eigenvalues of a sufficiently complicated quantum system should universally resemble the statistics of eigenvalues of a random matrix. So this idea kind of started with the work of Wigner, and the more precise version of it is known as the Bohigas-Giannoni-Schmidt conjecture. So it doesn't really matter what the details of the quantum system are, no matter what you have, as long as it's chaotic, the fine-grained statistics of the energy eigenvalues should resemble those of a random matrix. So that's an incredibly strong statement of universality. And just to give you a picture of what that looks like, here's a set of numbers on the real line that looks like a just Poisson distributed, so just sampled independently with the uniform measure on this interval. And at the bottom, you have exactly periodic set of numbers, and the statistics of energy eigenvalues of a random matrix look somewhere in between the two. So it's somewhere in between. They're random numbers, but they have a repulsion so that they don't like to be very close to one another. So they somehow intermediate between Poisson statistics and completely periodic lattice. Okay, so can we find these statistics in the spectrum of a black hole? Since if a black hole represents a chaotic quantum system, it should exhibit random matrix universality. So can we show that without knowing exactly what the eigenvalues are? Okay, so here's how one can try to do that. Given a Hamiltonian H, a convenient way to package together the energy eigenvalues is to compute the thermal partition function z of x, which is trace of e to the minus x times h. It's a sum over all the energy eigenvalues of e to the minus x times the eigenvalue. So this encodes all the energy eigenvalues. And just for an example of what this partition function, what we can do with this, let's take a very concrete example where H is the Hamiltonian of the SYK model. So that's some kind of ensemble of Majorana fermion systems with a 4 fermion interaction. These psi's are Majorana fermions, the j's are random numbers. So the SYK Hamiltonian is a sum over all possible 4 fermion interactions with just random coefficients. That's a particular kind of matrix, and it's a chaotic system, so we should be able to see this energy eigenvalue statistics there. And here's a plot that kind of illustrates how you can show that. So we compute something, a function of this z of x. It's called the spectral form factor, and it's a function of a parameter t that we think of as a time parameter. How is it defined? You take 2 copies of this thermal partition function z, and you take one of the copies and you evaluate it at beta plus it. So you analytically continue this x parameter to beta plus it. You take the other copy, you evaluate it at beta minus it, and then you take t to be large. And these angle brackets mean the average in the ensemble of SYK theories, for example. Okay, so what does that function of time look like? Well, it's this crazy red curve here. So it starts out big because we're summing over a whole bunch of eigenvalues. So it's a big number. It decreases with time because the presence of it here means that different eigenvalues will contribute with different phases, e to the I times eigenvalue times t. So basically, because of phase cancellations, the function decreases as a function of time. But then at late times, something kind of crazy looking happens. The function starts to get quite erratic as a function of time. And if you kind of smooth it out, either by averaging over time or averaging over realizations of the SYK model, different sorts of couplings, then this really erratic red curve becomes a smoother black curve. And it exhibits these distinctive features of a ramp, so a linearly increasing region, and a plateau. So this function does not keep decreasing forever. Instead, it exhibits this linear ramp and a plateau. And this particular pattern of this linear ramp connected to a plateau is a precise test of the random matrix statistics. So that particular function, of linear function ending in a plateau, is a prediction of random matrix statistics. And here we see a version of this Bohigas-Giannone-Schmidt conjecture, which is that this particular chaotic quantum system is indeed exhibiting that behavior. Okay, so we want to see if a black hole does that. Does a black hole exhibit a linear ramp and a plateau if we compute the spectral form factor? All right. So I'm going to show how that works in a particular very simple theory of a black hole. It's a two space-time dimensional black hole. It's called Jakiv-Teitelborn gravity. So here's how it works. So it's a two-dimensional theory of gravity where we have two fields. We have a space-time metric, a two-dimensional space-time metric, that's this G, and we have a scalar field phi. And R is the curvature, which is built out of G. So here's the action in Euclidean signature. We have a large parameter S naught. So S naught is just a number, but you should think of it as a large number that multiplies the Euler characteristic. So this looks a little bit funny. Why are we adding this Euler characteristic to the action? That's actually just the, this is the ordinary Einstein-Hilbert action in 2 dimensions. So just square root of G times R, that's the Einstein-Hilbert action in higher dimensions. That's a topological invariant in 2 dimensions called the Euler characteristic. So this term does not give any dynamics to the theory. So in 2 dimensions, people add this additional scalar field phi so that the full action has the Einstein-Hilbert term here, and then it has another term of square root of G times R plus 2 times phi. Okay, so that's the Jakiv-Teitelborn gravity action. And in order to study the quantum mechanical theory of the black hole, we want to do the path integral over these two fields, the scalar field and the metric, weighted by this action. Okay, and this is a simple enough theory that you can actually do this path integral. Here's how you do it. So in the first step, you do the functional integral over the scalar field phi. So you integrate over phi first, and we use a contour that's parallel to the imaginary axis. So if you think about taking the exponential of this action, integrating over phi, that integral gives a delta function. That's like an integral representation of the delta function. And so that gives a constraint that R plus 2 has to vanish everywhere in space, everywhere in space-time. So R is equal to minus 2 everywhere in space-time. And in 2 dimensions, fixing the scalar curvature is very constraining. It says that the metric is actually just a piece of rigid hyperbolic space. So huge simplification has taken place here. We integrated over phi. First of all, it was easy to do the integral. We just got this delta function. And second, the result of that integral helps us tremendously. It tells us that the integral localizes to just pieces of rigid hyperbolic space. Okay, so step 2, we just need to integrate over the appropriate pieces of hyperbolic space. So this step, this is now more of a sort of a classical math problem, less of a quantum gravity problem. So to compute the partition function, what kinds of pieces of hyperbolic space are we supposed to take? Well, the rule is that if you're computing the partition function z of x, then the boundary condition that we should put is that the space should have a boundary with length x. So an example of a configuration that would contribute is this region here. So here's the hyperbolic disk as drawn by Escher. And the infinite hyperbolic disk has a black boundary. And I've cut out a region with a red boundary. So it's kind of an irregular cutout region of the hyperbolic disk. And we're supposed to integrate over all such cutouts such that the length of the red boundary is x. That will compute for us as z of x. Okay, and this disk-like region of the hyperbolic space is a 2-dimensional black hole in Euclidean signature. Imaginary time. So what a black hole in imaginary time means is that the time direction is contractible. So the red circle here is the imaginary time direction, and you can see that it's contractible in space. Okay, so let's just think about this math problem. So we're supposed to integrate over all possible shapes with fixed length in hyperbolic space. And that's not too bad. You can parameterize the shape of the boundary here by some function. So you're doing a one-dimensional functional integral, and that integral can be done exactly, and we get the following answer as a function of the length x. So it's 1 over x to the 3 halves times e to the s naught. That s naught is just because the Euler characteristic of the disk is 1, plus pi squared over x. So the x dependence here is a little bit non-trivial and comes from doing the integral over the random shapes. Okay, to compute the spectral form factor, z of beta plus it times z of beta minus it, we're supposed to take this result and substitute in for x. In one factor, x becomes beta plus it, and in the other factor, x becomes beta minus it. So if you do that in this expression, and then you take t to be large, you'll find the following. You find e to the 2s naught divided by t cubed. So this term in the exponential just went away because t is large, and the two factors of x1 to the 3 halves and x2 to the 3 halves give us this t cubed. So this is a function that is decaying in time, and actually this matches quantitatively with this initial region where this function is decreasing with time. So this gives this initial decay, but if we follow it to very late time, it just decays forever. And this looks like a problem. It looks like a problem because the black hole computation is not matching with the expectations from quantum mechanics. Expectations from quantum mechanics are that it should decrease and then have a linear increase and then a plateau. And here we're just finding the decrease. So this is a version of the black hole information problem that was described by Maldacena in 2001. This is a version of an old and important problem that we're just getting decay here instead of the more complicated function. Okay, so what's missing?
Sorry, can I make a question?
Yeah, please.
So what's the physical intuition behind computing this product or partition functions? Is there a physical intuition behind this particular combination?
Yeah. Yes. Yeah, so the idea is that basically it's a good probe of the statistics of energy levels in the random matrix, statistics of eigenvalues. So if we take two copies of this thing, one with e to the iht and one with e to the minus iht, and we take t large, that will look a little bit like a Fourier transform over in the difference between the energy eigenvalues. So we're kind of summing over two energy eigenvalues, lambda1 and lambda2, or e1 and e2. And the spectral form factor, it's like a Fourier transform in the difference of the two energies. So as a function of time, it's sensitive to like increasingly strong and short range correlations between energy eigenvalues. And what you see here in this plot is that at sufficiently late times, when we're looking at basically very short range correlations with eigenvalues, this linear ramp turns into a plateau. So the early times here is like reflecting some kind of long range anti-correlation between distant eigenvalues in a random matrix. So if you pick an eigenvalue somewhere, then in a random matrix, that gives a kind of a weak long range power law repulsion to all of the other eigenvalues. So not just the nearest neighbor, but even very distant eigenvalues have a weak sort of power law decaying repulsion. And that particular power is 1 over delta E squared, and that corresponds to this linear ramp. So the physics of this linear ramp is the long range power law repulsion. And there's a transition to a plateau at some very late time. And that very late time corresponds to the inverse of the level spacing. So the closest spacing possible between eigenvalues, the nearest neighbor spacing. And the transition between the ramp to the plateau is kind of describing the statistics of the nearest energy levels. So that's the physics of the spectral form factor, and it's been studied for decades in the quantum chaos literature. People like to study it there as a probe of of these eigenvalue statistics. It's convenient also in the black hole case because it's related to, in a simple way, to the thermal partition function, z of x. So it's very simple to compute in a black hole. You just take this boundary, and you take the boundary to have length beta plus it. So it's kind of has a very simple geometrical interpretation.
I see. Thank you.
Okay. Yeah. Thank you for the question. Okay. So yeah, and so it's a simple quantity, but it's nice geometrical interpretation, integrate over everything with a boundary of length beta plus it. But we got the wrong answer. So the black hole computation gave the wrong answer. So what's missing? Well, let's think about this problem again. When we have two copies of the partition function, z of x1 times z of x2, as we do in the spectral form factor, then we could have two separate disks. That's this computation. That's actually the computation that we just did. But we could also have these two boundaries at opposite ends of a cylindrical wormhole. So there's a different topology that could contribute here. So a different topology for the two-dimensional space-time. And okay, so in parentheses here, there's some math. This is just the product of the two answers for the two disks. These are the functions that we wrote before, 1 over x to the 3 halves times e to the s naught plus pi squared over x. Two of those factors. That represents these two separate disks. But we also can have a computation on this cylinder topology. And I'm not going to go through that, but it's a simple computation. And this is the explicit function you get as a function of the two lengths of the boundaries, x1 and x2. So now if we take our, sorry, I should have written this here. If we take x1 to be beta plus it and x2 to be beta minus it and plug that into this formula, well, this is the decaying term that we found before. But the wormhole gives us something that is growing with time, and it's growing with time linearly. So these two contributions, the two separate black holes and the black holes connected by a space-time wormhole, these together describe the slope and ramp portion of the spectral form factor plot. So they confirm in detail this Ohigas-Giannoni-Schmidt conjecture for black holes, that indeed the eigenvalues of a black hole, even though we don't know where the eigenvalues come from in the space-time description, but we do know that they should exhibit this long-range power law repulsion that is associated to the ramp. So we don't know where the actual discrete set of eigenvalues comes from, even qualitatively, but we do know some of their statistical properties, and in particular, the statistical property that follows from quantum chaos. Okay, so how does the black hole manifest random matrix statistics? And the answer is wormholes. This is obviously a incomplete story. So what we really want to know is where the actual, honest to God, discrete set of eigenvalues come from. But it's non-trivial that black holes can reproduce this linear growth in such a simple way. Okay, so the final part, so this is part 3 of 3, is again a completely different subject where wormholes are going to play a role in a quantum, in making black holes consistent with quantum mechanics. So this is a famous story, the entropy of Hawking radiation, in particular, what's called the page curve for the entropy of Hawking radiation. So I want to start by explaining that. So the setting now is an evaporating black hole. So we don't have a black hole in anti-de Sitter space. It could be, but not necessarily. And the black hole is evaporating. So this is the space-time diagram for an evaporating black hole. The blue line is a time slice. So the region out here is outside the black hole, and the region inside here is inside the black hole. This time slice extends across this dashed line, that's the horizon, separates inside from outside. And this diagram is supposed to be a picture of what Hawking radiation looks like. So Hawking radiation can be thought of as arising from entanglement between quantum field theory modes just inside and just outside the horizon. And they're moving, let's say we're studying the modes that are moving to the right at the speed of light, And you have an entangled pair here, entangled pair of vacuum fluctuations. And the one that's moving to the right outside the horizon becomes a Hawking particle that reaches infinity. The one that's behind the horizon falls in and hits a singularity. So somebody outside the black hole just sees kind of half of this story. They see half of each Hawking pair, and that is what Hawking radiation is. So there's one pair, there's another pair, there's another pair, and at late times we get more and more of these Hawking pairs. So based on roughly this picture, Hawking computed the entropy of Hawking radiation. So that's the entropy of all these guys out here, all the ones that make it outside. And it just grows essentially linearly with time, proportional to the number of pieces of Hawking radiation that emerge from the black hole. Why is that the case? Well, each one is entangled with a partner behind the horizon. So each one is in a mixed state that contributes positively to the entropy. And so as time passes, we just get increasingly many sort of highly mixed pieces of Hawking radiation, so the entropy just goes up and up and up. Okay. This is a problem because this entropy represents entanglement between the Hawking radiation that's come out and whatever remains behind the black hole. So the entropy that we were computing of the radiation is in principle an entanglement entropy between the Hawking radiation and the black hole. And entanglement entropy cannot exceed the sort of number of degrees of freedom of the black hole. So as a function of time, the black hole is evaporating. So SBH, think of that as the number of degrees of freedom of the black hole. That's decreasing. It's like the area of the horizon of this evaporating black hole. So it's decreasing with time. The maximum possible entanglement entropy between the black hole and anything is this blue line. And it doesn't make sense for the entanglement between the Hawking radiation and the black hole to exceed that value. So this paradox was discussed by Don Page, and he proposed, well, the paradox was discussed earlier, but Page was thinking about this, and he made a concrete proposal that the entropy of the radiation should actually follow this curve. And his proposal was based on the properties of entanglement entropy in random states. So it should go up, and then it should go down again as the black hole gets smaller. Okay, so the question is how can this answer be derived from gravity? And I'm going to sketch one way it can be derived. And the version I'm going to explain emphasizes the role of space-time wormholes. So to understand that picture, it's useful to think about the entropy minus trace rho log rho. Rho is the density matrix. It's useful to think about that as using the replica trick, where we compute at an intermediate stage, we compute trace of rho to the power n. And then we take n close to 1 and take the derivative with respect to n. In other words, one way to compute the entropy is to first compute trace of rho to the n for an arbitrary integer n, and then endlessly continue close to n equals 1. So for integer n, we need n copies of the black hole geometry, n replicas of the black hole geometry, of the evaporating black hole. And in Hawking's calculation, in principle, he could have done it this way with n copies of the black hole, but the n copies are just completely disconnected from each other. And completely disconnected, so it's n separate black holes. But one can also consider a configuration where the n replicas are connected together. So kind of like, let me go back a second, kind of like in this picture, we can have disconnected black holes, or we can have a connected configuration. The same is true for computing the entropy. We can have n disconnected black holes, or we can have the black holes connected somehow by a space-time wormhole. And that's known as a replica wormhole. So I'm not going to show this in detail, but I want to emphasize what happens to these wormholes in the limit where we take the parameter n close to 1, because that's kind of an interesting and beautiful thing happens. I just want to explain that point. So, but for the moment, forget about black holes. We'll come back to it, but I want to explain this geometrical point first in a simpler setting, and then we'll discuss it in the context of black hole. So let's just think about this family of geometries for integer n. So the geometries have two kinds of boundaries. They have a black boundary and they have a blue boundary. The black boundaries correspond to the region outside the black hole. But here's a geometry with one black boundary and one blue boundary. So this is an n equals 1 geometry. Here's a geometry we'll call the n equals 2 geometry. It has two black boundaries. They're disconnected from each other, but they're connected by these blue boundaries. And if we think about the black boundaries as the physical boundaries of this system, then this is a wormhole that connects the two black boundaries together. It's a little bit like this cylinder diagram that we had before. Okay, that's for n equals 2. For n equals 6, we have 6 of these black boundaries, 1, 2, 3, 4, 5, 6. And we can consider this geometry that connects them all together like this. It's kind of a 6-copy generalization of the wormhole. We can consider these geometries for arbitrary integer n. And one thing to notice is that they have a Zn rotation symmetry. So if you look at this black dot here, then the geometries these pictures have a Zn symmetry rotating about this point. And that symmetry is important because if we quotient by this symmetry, then we get a geometry that family of geometries that looks like this. So n equals 1, 1 is the same. There's nothing to quotient by. For n equals 2 case, we quotient by the 180-degree rotations. So that gives us this geometry here. And if we take this geometry and quotient it by Z6, we get this geometry here. So we always get one boundary, and we got a conical deficit at the black point, at the locus of the Zn rotation symmetry. So these two dashed lines should be identified with each other in the quotient. An important point is that these quotients can be continued in n. So analytic continuation in this integer number n makes sense for these quotients. So here these geometries are defined only for integers, but these quotients are defined for arbitrary values of n. So in particular, here's a geometry for n fairly close to 1. We have a conical deficit that's small. And here's the geometry in the limit n goes to 1. So n equals 1 plus epsilon. We recover the original n equals 1 geometry, but now with a special marked point. The special marked point is the location where it's kind of the avatar of the quotient. It's an avatar of this generalization n of these wormholes. So the limit n goes to 1 of this quotient gives us back the original geometry, but with a marked point that is kind of the only leftover feature of these integer family of wormholes. Okay, so that's the point that I wanted to explain here. Now let's try to relate that back to the black hole computation.
So can you remind what the blue boundaries?
Yeah, the blue boundary is should think of it as the region behind the horizon of the black hole. So this black region is like the boundary of the black hole, an Euclidean signature, and the blue region is the region, something behind the boundary of behind the horizon of the black hole.
Thanks.
Yeah. I wouldn't try too hard to make this geometry match precisely with the black hole. The only thing I want you to understand here is the connection between these integer family of connected geometries, wormholes, and the limit n goes to 1 being kind of like a marked point on the original geometry. So when we take n copies of the evaporating black hole, then to compute the entropy, we can do the same kind of thing. And we can consider a connected wormhole geometry and take the n goes to 1 limit of the quotient. And that becomes a point very close to the horizon of the black hole. So the analog of this black Zn fixed point is a point very close to the horizon of the black hole. This is called the quantum extremal surface. This is the quantum extremal surface. And the formula for the entropy is basically the area of this surface. And so this quantum extremal surface technology is basically this argument I made on the previous slide is made by Faulkner, Lukowitz, Maldacena, Dong, and Lukowitz. And well, sorry, in this context, it's made by these authors. It's an older argument. And when applied to the evaporating black hole, it's shown by these authors, Pennington, Almhiri, Engelhardt, Marolf, and Maxfield, that that Zn fixed point becomes a point that is close to the horizon. The quantum extremal surface becomes close to the horizon. And the fact that it's close to the horizon gives you the page curve. So that gives us this function here, where the entropy decreases. So the entropy that you compute is basically the area of that special point, of that quantum extremal surface. And because it's close to the horizon of the black hole, it decreases in lockstep with the decrease of the area of the black hole. Okay, so that this is a sketch of the logic behind the computation of the page curve for an evaporating black hole. But I encourage you to look at the literature for a clearer description. So a question that's been bugging people, in particular since the 90s when Page wrote his paper, is what was it that Hawking missed in the calculation of the entropy? His entropy formula was just increasing, and we believe the right answer should go up and then go down again. And the preliminary answer, based on the work of the authors I cited a second ago, is that basically Hawking left out the wormholes that could connect together the different replicas of the evaporating black hole. Okay, and I have let me not discuss the puzzle, and just thank you guys for your attention and for the questions.
Okay, thank you very much, Doug, for this very interesting talk about black holes. And if there are any questions in the audience now, so please raise your hand or write your question in the chat. I'll maybe start with a question here. So you mentioned that well, this problem of the eigenvalue, that the decay of the form factor, the naive form factor, was some kind of manifestation of the information paradox.
Yeah.
So what's the connection with information paradox in this case?
Yeah. So there's a version of the black hole information paradox, which is due to Maldacena from 2001, and his version of the black hole information paradox is kind of an experiment you could imagine doing, where you, instead of computing the entropy of the Hawking radiation, which is Hawking's information paradox, we just compute a very simple observable, which is the two-point function, autocorrelation of some fields outside the horizon. So we measure the field at time 0, measure it at time t, and compute the autocorrelation. And in a finite entropy quantum system, that should not decrease forever. It should reach some floor value e to the minus s and kind of rattle around. In finite entropy systems, you basically can't completely decorrelate variables. But for the black hole, it seems to just decrease forever. And that's basically what this spectral form factor is. Is computing. You can think of it as being essentially the two-point autocorrelation function. Like if you think about a two-point function 5, 0, 5t, there's one copy of the time evolution operator to go up from 0 to time t, and another copy of the time evolution operator to come down from time t back to 0. And those are related to the two factors of e to the iht and e to the minus iht in the spectral form factor. So the initial decrease of the spectral form factor is like the just decay forever of the autocorrelation function in Maldacena's paradox. And the linear ramp and plateau is something that is supposed to fix that up in a finite entropy quantum system. So that's the relation between those things.
Okay. Are there any questions, guys? I have another one related to this topologies that contribute to this form factor in particular, right? Or also in the case of page curve, you need to consider different topologies. So there is this issue about these topologies not being classical solutions of the action, so they are not extreme.
Right.
So what's the philosophy of this? Why they should be taken into account in the first place?
Okay, yeah, good. So for the case of the evaporating black hole, they are actually classical solutions. For the case of the spectral form factor, they are not classical solutions. And, well, sorry. There's a version of the computation for the spectral form factor where you study it at fixed energy instead of fixed beta, where it is actually a classical solution. So these hard topologies, okay, so that's a detail, that there's a version of this where it actually is a classical solution. But let me try to answer the spirit of your question, which is whether you should take seriously wormhole geometries that are not classical solutions, because they certainly exist. And in general, to take those things seriously, you need better control over the bulk theory. And in some examples, we have that, like in JT gravity or dilaton gravity theories, or maybe in 3D gravity, we understand the bulk theory well enough that we can consider off-shell configurations and do the path integral. But for more interesting theory, we don't know how to do that. So that's a challenge. There's some work by Kotler and Jensen and using the language of constraint instantons to analyze those things. So even if something is not a classical solution, sometimes it's close to a classical solution, and the wormholes have that property that there's just basically one degree of freedom or a finite number of degrees of freedom that are off shell, and you can put everything else in the functional integral on shell and then just integrate over this small number of off shell degrees of freedom separately. So there's some like field theory techniques for trying to analyze those off shell configurations, but in general, it's more challenging. However, just to repeat, for the page curve for the evaporating black hole, none of that is necessary because the wormholes are actually honest on-shell solutions.
Okay, I guess my question was really about, there seems to be like way out of the standard paradigm where you should sum over classical solutions over classical saddles in the path integral. And I was wondering, of course, this is not my question. I heard this question about this exact topic before, and I was just wondering if there's any new view of why this kind of configuration.
Well, I don't think the paradigm is that you're supposed to sum over classical solution. I think the paradigm is that you're supposed to do, in principle, the bulk computation, and the bulk computation is a path integral, sum over topologies and a path integral. And in some cases, the path integral has a classical solution that gives the effect that you want, and that's a little bit easier to analyze. In some cases, it doesn't. And the configuration that you're interested in is not a classical solution, but it's still a contribution, still contributes to the path integral. So I don't think we're changing. It's not a change in paradigm. It's a technical difference of whether one is kind of understands the theory well enough to take seriously slightly off-shell configurations or not.
Okay, thank you. So there is a question from Edson Moreira. Edson, please ask your question.
Thank you very much for your talk, Douglas. I was wondering if when you are working with black holes and the parameter beta is the inverse of Hawking radiation, and in that model of matrix that you show us, appears a period in beta, I plus I beta. Is there any interpretation, geometric interpretation for that beta there, like inverse of Hawking radiation or something like that?
Yeah, that's right. So that beta is, in that expression, is still interpreted as an inverse temperature. So the spectral form factor is really a function of two things: time parameter and a temperature-like parameter. And the temperature is 1 over beta. So it's just what you said, that the beta in that expression has the interpretation of the inverse.
But it doesn't have to be Hawking temperature or some geometrical temperature. Like, for example, when you work with black holes, either you work with the Hawking temperatures, otherwise you have a conical singularity. In that case, there is no, I mean, you don't have to use a particular value for beta in order to avoid some kind of defect in the geometry or something like that. Is that
right? Good point. So if we're just computing, let's say the thermal partition function of ordinary, just one black hole, then you could fix beta to anything you want, but the energy of the black hole and the area of the horizon will be determined by the condition that you said. It will be determined by the smoothness of the horizon. So it will be determined by periodicity, locally looking like a smooth point. So that relation determines the energy of the black hole in terms of your control parameter beta. You can take any value of beta, but the solution will determine the value of the energy so that it's smooth. The geometry, the constraints are a little bit different on the wormhole topology. So on the wormhole topology, it's not the case that the beta parameter determines the energy in the same way. And actually, yes, let me answer your question. It's related to the previous question, so let me answer it in a slightly different way. Let's consider not fixing beta and instead fixing the energy. Let's fix the energy instead of the temperature. And then what you said, the property you said, would fix beta in the standard computation. So we fix the energy of the black hole, and then we find out what the inverse temperature is, what beta is. For the wormhole, the geometry is different. And basically what you find if you fix the energy is you find beta equals 0.
All right.
So for any value of the energy, the corresponding beta should be 0. And that's the classical solution on this wormhole topology.
And that would affect in somehow the entropy of the whole system?
No, it's just that on this topology, the connection between energy and temperature is very different. So on the leading topology, on the disk,
Yeah, but in usual black hole, you have the associated entropy to the Hawking radiation, to beta is the Bekenstein-Hawking entropy. Is there anything like that in the case of wormholes?
Well, so if the usual computation you're referring to is determining the entropy of the black hole as a function of energy or temperature using the relation between energy and beta. And that's something that you do once and for all on the disk topology. And that determines for you the entropy function. The wormhole computation does not give you a new entropy function. That's already determined by the disk topology. It's just so it doesn't tell you something new about the entropy as a function of energy or beta. It's just that on that topology, the connection between beta and energy is different. It's like, suppose we have an ordinary quantum system, and we compute some quantity that's sensitive to very low energies. Then I think if I try to say more, it will just lead to more confusion. I don't know if you want to ask another question, I could try again. But yeah.
Thanks a lot, Doug.
Yeah, thanks for the question.
So there are a couple questions on YouTube. I'll read them. One is from Deepak Vaid. Is about well, he asked you about the Entanglement Island and where it comes from. If you can explain it in simple words, or
yeah, the Entanglement Island is the region. It is the region. Let me put this back up and then go back. So the island is this region here. It's the region between on the other side of this quantum extremal surface, and the physical interpretation of this computation that these folks did is kind of an amazing thing. It says that this region here, this island region, is actually encoded in the Hawking radiation, which is way out here. So the Hawking radiation that has come out of the black hole previously somehow is a description of the region behind the quantum extremal surface, this dotted line. I'm not sure if that's the question that was being asked, but that's what the island is and what its interpretation is.
Okay, thank you. And another question is from Ricardo Medina, who is asking how essential the string theory in all this, on all these calculations.
Yeah, it's not essential. So these computations that I did here use they use general relativity, so that it doesn't depend on any particular features of string theory. The role that string theory has played is that the cases where the connection between black holes and quantum systems is understood precisely are cases where the black hole is a black hole in string theory. So string theory gives us confidence that this relationship really exists and makes sense mathematically, but the details of these three examples depended only on the low energy physics. So they don't depend on the UV completion of the bulk theory to string theory or to something else. It might be, in fact, it's very likely that the things that we have not yet understood, like what are the specific energy eigenvalues, what physics is related to the specific energy eigenvalues of the discrete nature, that probably does depend on more UV data and would depend on string theory or the UV completion of the bulk theory, but the things that we discussed in this talk do not.
All right, thank you. Well, there's one more question on YouTube, but I honestly cannot understand the question itself, so I will skip it. Let me ask maybe a final question. So, well, you decided not to tell us about the new puzzle. If it doesn't take another 10 minutes, maybe you can briefly tell what the puzzle is.
Yeah, the puzzle was just where does this crazy red curve come from? So here we've understood this smooth decrease and then a linear growth, and those things we understand from the space-time geometry, and it's a simple explanation in the topology of space-time. But in principle, for an honest quantum system, you shouldn't get that exact kind of smooth function. You should get this crazy erratic red function. And so the puzzle is, where does that come from? Where does that function come from? So this is basically not asking for the statistics of the energy eigenvalues, but for their actual values. And yeah, it's an important problem. And the extent to which it's not understood is is close to 100%. So yeah, that was it.
All right. So thank you very much, Doug, for your talk, and thank you very much, everybody, for participation. And we'll have a small break in our seminar, and we'll have more talks 3 weeks from now. And I invite you back here in the seminar in October 10. Thank you very much, and take care.